we already talked about the concept of subjective probability, and the main message was that most probabilities in real-life problems are subjective. They are not estimated from relative frequencies because either you are dealing with one-time events or there are rare events that are happening, so you cannot estimate relative frequencies. And the second message was that there is a procedure based on a logic, concrete logic, to estimate probabilities, subjective probabilities. So now, let's consider problems where you estimate continuous probabilities. For example, a probability distribution function is a continuous probability. It's a number that varies continuously. So let's say that you want to estimate your final score in this class. The score will be, the final score will be between 0 and 100, okay? So what we'll do is assess the probability that the student's grade will be below a certain value or equal to a certain value, say 95%. So you estimate or will estimate these probabilities, okay? And this, of course, will be done for a fictitious problem. So you'll estimate a number of probabilities for different scores. For example, you'll estimate the probability that your score will be less than 99%, the probability that will be less than 95%, the probability that will be less than 80%, and so on. So you'll get a lot of points, and then you'll connect them and get a curve that represents a cumulative probability distribution function of your score. Okay, so here is the procedure to estimate the probability that the grade will be less than a certain value. We consider two alternative bets. So this is bet 1. Okay. So let's say you want to estimate the probability that your score will be less than 80%. Well, then you have this bet. Imagine this bet. Okay. If your final score is less than or 80%, let's say you get a free car. Let's make it more attractive and say this is a free Mercedes-Benz S-Class, okay? S-Class is the top model, all right? And if the score is above 80, then you get a free movie ticket for a movie theater. So, free movie ticket. So this is one bet. And the alternative bet is this is bet 2. You consider a wheel of fortune. Okay. So the wheel of fortune is a big wheel, and you have an arrow, a needle, and you spin the needle, and then the needle stops at a certain point. Okay? So this is the well-oiled and balanced Wheel of Fortune. Okay. So you divide this into two regions. This is region A. So this is A, this region. And the rest of the region is A prime. Okay? So you can adjust the probability of event A, that means the needle will stop at A, by increasing the size of this sector. Okay? So what is the ratio of A over A prime? Well, this is equal to the probability that the needle will stop in A over 1 minus this probability. Okay? So as you make this sector, this bigger and bigger, the probability also increases. Okay? So now the second bend involves spinning this this needle. Okay? So if the needle stops in sector A, then you get the free current. Okay? So you get your free Mercedes-Benz S plus. All right, that sounds very interesting. And then if it stops somewhere outside this sector, you get the free moving ticket. Okay, so you compare the two bends, okay? And what you do is adjust A, this sector, until the two beds become equivalent. That means you would exchange this ticket that corresponds to this bed with the other one and vice versa, okay? So you are asking yourself, for what probability P, okay, which is proportional to this area, the two bets are equivalent. That means you have the same probability to win one or the other. Okay. So, what the question that you ask yourself is, what area A makes the two beds equivalent? Two beds equivalent. Okay? Let's say that the student is not very confident that will do well in the class. Okay? So it's unlikely to get, the student thinks that it's unlikely to get a score that is higher than 80. Okay? So let's say you have a weak student. So in that case, the probability that the score will be less than 80, which is this event, okay? The probability that grade will be less than or equal to 80 will be very high, unfortunately. And therefore, the probability that makes this bet equivalent to this would be very high. So P is very high. Okay. So you do this approach several times for different grades. So you start from 80, you find the probability that the score will be less than 80. Then you change the score, you make it 90. You find again the probability that the score will be less than 90. And you repeat this process until you have enough points that you can connect to find the cumulative distribution. So if you find that the probability that the grade would be less than 80, say it is 90%, then this means that 80 is the 0.9 fractile of the distribution of the score distribution or 80 is the 90th percentile of the distribution. Okay, there is a name for the 50 per fractile, 0.5 fractile. That means the value for which 50% of the population is below and 50% is above. This is called median. Okay. So for the median, 50% of the grades are above it. And the rest 50% below. Okay, so in the end you will come out with a cumulative distribution of the grade so cumulative probability distribution of grade say it looks like this. Here we have the grade x, and here we have the probability to be below, which is what we call the cumulative distribution of the grade. So let's say that 50 is the lowest possible grade that the student thinks that will get. Then we have a value for 70, and that will have a probability, say 50%. So this is 0.5. Then if you look at 80, the probability, say, to get below 80 or exactly 80 is 90%. So this student is not very confident. So this probability is 0.9. And then the probability that will be less than or equal to 100, well, this is the certain event, and the probability of that certain event is certainly 1 for every 1. Okay? So this is 1. Now, you can connect the dots, and then you'll have a shape of the cumulative distribution of the grade. So it will look like this typically. It's monotonically increasing from 0 up to 1. So you have a curve like this. This is the cumulative probability distribution of the grade. All right. Back in 2004, when I was teaching the class for the first time, we estimated the cumulative distribution function of the Dow Jones Industrial Average a few days later. So the class was, say, on Tuesday, and we estimated the value of this index, the Dow Jones Industrial Average, for Friday. And then we looked at this distribution and we compared it with the value that was estimated. So, cumulative probability distribution of the Dow Jones Industrial Average next Friday. And this was done again in March 2004, 10 years ago. Okay, so we assessed the 5 percentile, 25 percentile, 50, 75, and 95 percentiles. So assessed 5 percentile, 25, 0.5, 0.75, and 0.95 percentiles, which are fractiles. And then we connected them with a smooth distribution, okay? And we found that we started with this fractile, 0.05. So the probability that the Dow Jones Industrial Average, we ask ourselves what value has probability to be below corresponds to probability of 5%, and that was 9,500. So basically, we thought, the professor and the class, that is very, very unlikely that the Dow Jones Industrial Average a few days later would be less than 9,500. We also went and estimated the high fractile. That means a value that is very, very unlikely to be exceeded. So we found that this was 11,000 after some thought. 11,000. So the probability that the Dow Jones Industrial Average will close below 11,000 is 95%. Okay? So almost certainly it will be below this number. Then we looked at the median, which is the probability, corresponds to the probability of 50%, and the median was estimated 10,300. So there is 50% chance to be below 10,300, 50% to be above 10,300. Okay? And we continued with some other fractiles, the probability that the Dow Jones Industrial Average closes below 10,000. We felt that this is 25%. So it's kind of, the odds are against the closing below 10,000. All right. We produced a curve, a cumulative distribution, and before we continue and show the cumulative distribution, let's see what was the closing price. So when we got the closing price on Friday, we could tell how it compared with our estimates. Okay? So the closing price on Friday March 19th, 2004 was 10,186. Okay, this is the value that it closed at the end of the day on Friday. Okay, so this value, 10,100, is between the 50 and the 25 percentiles. So here was the true value, 10,186, true value. Now, if you look at this, is there any reason to say that our estimates were bad? Not really, because this is within the main body of the probability distribution. If we had, the value instead of 10,100 had been, say, 8,000, then that was bad, because we said that there is only 5% probability to be below, to close below 9,500. If it happens to be 8,000, then there are reasons to suspect that we didn't do a good job. Or maybe there was some catastrophic event. Okay, so let's see the probability distribution, our estimate, and how it compared with reality. Okay, so here are the estimates, our estimates in the beginning of the week, and the number that corresponds to the value of the index in the end of the week, on Friday afternoon. So we thought that the range would be between 9,500 to 11,000, okay? And 90% of the probability, with 90% probability, the Dow Jones Industrial Average will close in this region between 9,500 and 1100. These are the probabilities to close below its value. And then here is the true value. Well, this is in the body of the distribution. The true value is between the 25 and 50th percentile is about, I would say, about the 30th percentile. There's no reason to think that something went wrong because this is a reasonable value. Had the index been somewhere here, below 9,500, the estimate would not be very accurate. So this was a good exercise in terms of learning how to to estimate different probabilities of events that occur only once. Okay. We said that we use subjectivity to estimate probabilities in most real-life situations. And now we got to be careful because sometimes there are biases that unwillingly we just have when we estimate probabilities that different events may materialize. And many times we use heuristics. Heuristic refers to a rule of thumb. These are very useful. We use heuristics when we do a lot of different tasks like walking, driving, but we got to be careful because sometimes they create biases. For example, we may underestimate the probability of an event, or we may overestimate that probability thinking that it's highly likely, when it's not. One of the biases is the representativeness. Okay? If we think that if something has similar characteristics with members of a category, then it belongs necessarily to that category. Okay? So something belongs to a category because it has similar characteristics with its members. Okay. For example, let's say that a crime has occurred and the police is investigating the crime, and in the past people in a certain that share certain attributes, say young males, they have committed sometimes types of crimes, and they the police considers a suspect who has similar characteristics. Is a young person. So because of that, because simply has similar characteristics, the probability of having committed a crime is overestimated. Okay? So we got to be very careful about this. This is not a good way to assess probabilities and make decisions. Another heuristic is the availability. Something is something, some event, has high probability because it is easy to imagine. Okay, this heuristic may be useful, but we got to be careful. Sometimes may be very misleading. What is an example that there is something that is an event that is very unlikely to occur, but we overestimate its probability? Well, one is the airplane accident. We see every time that there is an airplane accident, we see in the news pictures that are terrifying, and because because of looking at these pictures and because they are quite strong emotionally, it is easy to bring this image in our mind. And then we think, because of that, the probability of an airplane accident is very high. That could be very far, this is very far from the truth. Flying is one of the safest way to travel. Very rarely accidents, airplane accidents occur. So this concept here, this heuristic, many times makes people to overestimate probabilities and make wrong decisions. An example was back in 2001, after September 11, when people saw all these pictures of horrible events happening, they thought that the probability of an aircraft accident was very high. And then they started driving, and guess what? Driving is far, far more risky than flying. The probability to die if you drive, well, there are 40,000 deaths because of car accidents in the US every year. How many people die in airline accidents? Usually no one, for several years. So some people, because of these events that were very unfortunate, they started driving instead of flying. And what was the result? In the following months after September 11, there were about 1,000 more accidents on deaths because of car accidents that year. So be very careful with this kind of biases that lead to overestimation of probabilities. Another is the motivational bias. Motivational bias, okay? This, the word actually says what it is. We want something to occur, and then we overestimate the probability, because, again, we want this to occur. A student, for example, may want to get a grade above 90, so because the student wants to do that, then overestimates that probability. We got to be careful about it. Another bias, another example of motivational bias is research results. Some people get some results, and without double checking or validating the results, they become very confident and they are willing to oversell the results to other people, write papers and so on. So an example of this is research results. Okay. Another bias is overconfidence. When someone is overconfident, underestimates uncertainty. So someone who is overconfident may think that can predict the value of the Dow Jones Industrial Average with very, very high accuracy. So someone may underestimate the variability and say that, you know what, I'm very certain that the Dow Jones Industrial Average will close between say 16,950 and 17,050 by the end of the week. So someone, because overconfident, thinks that can predict the stock market, the index, with very high accuracy. Most of the time, this is wrong. The variation actually is much higher than what someone expects, okay? And when someone is overconfident, the result is that makes very bad decisions. Okay, the final part in this lecture will be to estimate probabilities of events by decomposition. One method to estimate probabilities of events is to decompose the event into other, to break it down into other events, and then estimate the probabilities of these events. So decomposition. For assessing probabilities. Okay. I think of this as a process where you break down the problem into smaller pieces that are easier to solve. That's the idea of decomposition, okay? The approach is to think of probabilities of events whose probability we want to estimate. We think of or identify outcomes which would potentially lead to the outcome in question. Identify outcomes that might have happened before the outcome in question occurs. Okay, so this is the approach that we follow. We have one event, we think of other events that can contribute to the occurrence of that event in question, and we estimate their probabilities. So we identify the outcomes which finally can cause the outcome in question to occur, or we identify outcomes that may have happened before the outcome in question occurred. And we'll show this approach concretely in estimating the probability that there will be a death in a house fire. A house catches fire, and then what is the probability that the occupants will die? What is the probability of death in a residential fire? Of death in residential fire. Okay, so we consider an event 3 starting with a fire. Let's say that there is a fire in a house, okay? The next event to consider is, well, will the smoke detector work or not? A lot of things depends whether the smoke detector will work and alert the residents about the fire. So we consider the case where smoke detector works or not. Smoke detector working. So there is one path in case that it's working, which is good, and the other path if the smoke detector is not working, okay? So if it is working, then the next question that we ask is, will the occupant be able to escape? So occupant escape So the occupant may escape, which is good, or may not be able to escape because maybe the fire was too close to the location, or the occupant was fast asleep. In the other case, where the smoke detector does not occur, and we'll see how to estimate the probabilities that the smoke detector will work or not. Well, if it doesn't occur and you have a fire, still you ask yourself, will the occupant will be able to escape? And one possibility is that yes, will escape. The other case is that will not escape. Okay. Then we'll leave some space here for the probabilities, the final probabilities of each path. We have 4 paths, so we'll estimate the probabilities. And then the final consequence. Okay. So we can, before estimating probabilities, we can fill out the information about the consequences. If the smoke detector works and the occupant is able to escape, then this is nice and there's no injury. No injury, that's the final outcome. Okay. If the occupant is trapped, is not able to escape, which means that there's a death, or more death, there are deaths, okay? That's unfortunate. We have also this path that the smoke detector will not work, maybe the battery was too old. So in that case, if the occupant still is able to escape, you may have severe injury. And otherwise, if he's not able to escape, this is death. So we have this event 3 here, which breaks down the different events into other events that are easier to analyze and estimate their probability. Okay? So before we continue and calculate the probabilities, we consider what will happen, why the smoke detector may fail to work, okay, and assess probabilities. And this is done by, again, breaking down different events into other smaller events. Okay, so we consider what is called the fault tree, which tells you what can go wrong. So, one bad thing that this can happen is that the smoke detector is not working. Smoke detector not working. Okay. And we'll call this event E1. Okay. And this can happen in 2 ways. Either the battery is drained, okay, or there is a malfunction, okay? So someone may find it easier to estimate its probabilities. For example, the probability that the battery is drained. 10% of the time, a battery is drained and the owner of the house didn't bother to check and replace the battery. And the malfunction, the estimate is that the probability of a malfunction is only 2%. Okay? This is the first event. Okay? So the probability that from that you can find the probability that the smoke detector will not work, and put it back in this event tree. All right, let's consider the other outcome, which is the occupant will not be able to escape. So occupant did not escape. Okay. This is called event E2. The occupant did not escape. Okay. And this is occurring if we consider the case that will not be able to escape, given that the smoke detector actually worked, but still the occupant did not escape. So this is conditioned upon that the smoke detector actually worked. Okay? So E1 is that the smoke detector failed. E1 bar means that it worked. Okay. So this will happen if this case where the occupant could not escape will happen if the rescue effort failed. Rescue effort failed. Okay, and we'll put here a name. The occupant was trapped in fire. Occupant trapped in fire. Okay, and if both bad events happen, then the occupant is trapped, cannot escape. All right, now, occupant trapped, two things may cause that. So this is a norm. One reason could be because the fire was too close to the occupant. Fire too close to occupant. Okay, and the other cause could be that the occupant failed to wake up. So although the smoke detector worked, the occupant was not able to wake up. Okay, so occupant failed to wake up. Okay, so this is the second scenario in which the smoke detector worked, but the occupant was unable to escape. Now we're going to estimate the probabilities of these bad events. So there is a 50% probability that the rescuers will not be able to assist the occupant. Okay? Then the probability that the fire is close to the occupant is 10%. Okay? And the probability that the occupant failed to wake up is well, we need to break down this event. So we have an entity statement here that occupant was asleep and occupant failed to wake up. Did not wake up. Okay. The probabilities of these two events are estimated to be 50% that the occupant was asleep and failed to wake up is 0.2. Okay? So the probability of this event, which is the intersection of the two, will be the product if the events are statistically independent. Okay, now this is the second scenario where the alarm worked, but the occupant somehow failed to escape. And then we'll consider the last scenario. This is the occupant did not escape given that the smoke detector did not work. Okay? So this will be marked as E3, event E3. And this can happen if we have an end statement here, if the rescue effort failed, and the occupant trapped in fire Then we have the occupant trapped happens if the escape route was blocked. So, escape route blocked. Okay. Here we have an or the occupant failed to take escape action. Occupant failed to escape. Okay. And then there is an end statement here that means two bad events should occur. The occupant was asleep. And the occupant failed to wake up. Failed to wake up. Okay? A lot of things are common between this fault tree and this, but the probabilities are different. So let's put the probabilities. The probability of the rescue effort, that the rescue effort fails is 50%. And this is the case where the occupant, the smoke alarm didn't work. Okay? That's why the probability is so high, 50%. In this probability to escape, that the escape route was blocked, it's 40%. And then these two probabilities that the occupant was asleep is 50%, and the probability that failed to wake up is 30%. Okay, so now we have broken down events into other events, and we have their probabilities. Okay, so let's go back to the original event tree and calculate the probabilities. So the probability that the smoke detector is working is 0.882. How do we find this probability? We consider the probability that the battery is drained, which is 10%, and the probability that there was a malfunction, which was only 2%, and if we combine them, you get this probability that it will work. The probability that it will not work is about 12%, 11.8, to be more precise. In this event, we call it E3, that the smoke detector is not working. So this is E3. And we already estimated this probability from the fault tree. So this is E3. Now, the probability that the occupant would be able to escape, given that the smoke detector works, is approximately 91%, 0.905 more precisely. And the probability that although the smoke detector will work, but the occupant still was unable to escape and died, is the remaining probability, 1 minus this probability, which is almost 10%, 0.095 more precisely. Okay? And if we continue, the probability that, given that the smoke detector did not work, the probability that the occupant will escape is 75%, and the probability that will fail to escape is 0.245. So we have the 4 scenarios, and here are the consequences. In the first scenario, this is the best, there is no injury. The second scenario, the smoke detector works, but the occupant failed to wake up and escape, and this is the consequence is death. The third one is that the smoke detector failed, but the occupant eventually was able to escape, and in this case, it's predicted that the occupant gets severe injury. And in the last case, where the occupant is trapped, the smoke detector didn't wake him or her up, we have death. Now, if we combine the probabilities, then we can find these probabilities. So the probability that the occupant escaped without injury is 0.798. Okay. So there's about 80% probability if there is a house fire, no injury, no death to occur. Now, in this case where the occupant was trapped, this has probability of 8%. Okay? Then the probability of severe injury is also almost 9%, and then the probability of death is 0.29. Okay. So we have broken down the different events if there is a house fire, and we can calculate the probability of the death, which is the sum of these two probabilities. Okay. These are disjoint events. They cannot occur simultaneously, so their probability is the sum of the individual probabilities. So the probability of death is 11.3%. That's the bottom line. Okay. So what is the lesson from this? The lesson is that sometimes it's difficult to estimate probabilities of events directly. So if someone asked us, what is the probability that we have a death in a house fire? It's difficult to estimate that it is 11.3%. But if you think about how can this happen, and you follow the different scenarios, then it is easier to calculate probabilities of events. For example, it is easier to estimate the probability that a smoke detector will not work. That is not difficult to do if you have data from companies or from fire departments. And by doing that and using probability calculations, you calculate and assess risks. Okay, so this is a lesson that although a probability of an event may be difficult to estimate, if you are able to break it down, that event, to a sequence of other events, you estimate the probabilities and then you calculate the probability of that important event after that. Okay, so let's stop here.